All right, I hope you all managed to get through at least part of those questions. I'm going to take a bit of a jump now into Markov chain Monte Carlo methods, which arose in the 1950s, I think, originally for statistical mechanics, and were used in that field for a while. And statisticians didn't really pick them up very much, and computers weren't really that fast back then. But when they were rediscovered when these methods were rediscovered in the 90s and the late 80s and early 90s, I think they started to become very popular, and everyone noticed that they could be used to do all the integrals that pop up in Bayesian statistics. So that's kind of what led everyone in the 90s to start doing Bayesian statistics, was the fact that these computer algorithms let you solve the problems that previously would have been very difficult to solve. So I'm going to discuss the Metropolis algorithm, which is a kind of canonical algorithm of Markov chain Monte Carlo, and many other algorithms are kind of special cases or different twists on the Metropolis algorithm. So if you understand Metropolis, you understand a lot of what forms the basis of other Markov chain Monte Carlo methods, as well as just Metropolis on its own. You can solve quite a few problems with it. I won't be teaching specific software packages, though they exist. So here's a few that you might have heard of. I put DNest4 there because it's mine. That doesn't mean you have to use it. It's good if you know C++, bad if you don't. There's MC. I don't know if Dan Foreman-Mackey, who wrote MC, will ever watch this clip, but once he put me in one of his slides with the fake moustache, and it didn't really bother me, but that's just my excuse for what I'm about to say. I'm getting back at him. I would say the algorithm that underlies MC is only good in low dimensions, and it's become extremely popular in astronomy to use this MC package because it's a good piece of software, but I reckon there's probably some papers out there with wrong conclusions because they haven't noticed that the algorithm that underlies it doesn't perform well in high dimensions. So if someone wants to go through all the citations for that paper and find out where people were using it on high dimensions, might be a good way to find some wrong results in the literature and get published. There's Jags and Bugs. These are software packages that statisticians have used and that astronomers have hardly used. I think that a few use them. These are software packages that are good because you don't have to write quite as much code as we're going to have to write. So you don't have to write a function to evaluate the likelihood or a function to evaluate the prior density, which is two functions we'll have to write for each problem based on the code that I'm going to present you. The Jags and Bugs languages actually let you write down your assumptions like a statistician would, so using that twiddles notation. So if you have a problem, you have a parameter called lambda, like in the questions, and you wanted to assign a uniform prior, say, you just write lambda twiddles a uniform prior with some limits, and then your data, say it's Poisson, like in the examples, you could just write that x twiddles Poisson with mean or with parameter lambda, and you can just write out all your assumptions in that twiddles notation instead of having to worry about what the formula is for a Poisson distribution or whatever. And so Jags and Bugs are very good for fast implementation of different assumptions. Multinest is nested sampling, which I'll be covering a bit later. And Stan is kind of, it's along the lines of Jags and that kind of thing, but it's got different MCMC methods underlying it. It's got Hamiltonian MCMC, which has some nice properties. And I think Ewan might mention it on Thursday, though I'm not sure. But today I'm just going to go over the Metropolis algorithm, which is relatively simple and worth understanding. So the ingredients that you need to do a Bayesian analysis, we've already looked at this. So you've got a parameter space, you've got a prior distribution, you've got a likelihood function, and you want to calculate the posterior distribution, and ideally it would be nice to calculate the marginal likelihood as well, though it turns out that Metropolis cannot really give you the value of the marginal likelihood. So you'll be able to say things about the posterior distribution, but not the marginal likelihood. So if you want to do Bayesian model comparison, which I'll introduce later, you have to use something else. And this is just an example of the connection, which I mentioned to a couple of you, between the maximum likelihood method of estimation and Bayesian inference. So the maximum likelihood method, if you've seen it before, is one where you write down the likelihood function as a function of your parameters, and then you find an estimate of your parameters by finding the value of the parameter that maximizes the likelihood. So usually that corresponds to finding the best fit in the parameter space. So here's just an example of a single parameter theta, blue prior, light blue dotted likelihood, and a red posterior, which is the product of those two, but normalized. And Bayesian inference is based on that red distribution, whereas maximum likelihood estimation is based on just optimizing the likelihood function, finding the best fit. So that would give you that star point there. And the difference between the two is often minor. It depends on whether it matters, whether you just have a single estimate of your parameter versus whether you have a whole distribution. Does that make a difference for you? In some cases, it might not matter, and you might just be fine with finding the best fit. That's fine. Also, in high dimensions, the maximum likelihood and the posterior distribution can tend to give you different answers. So I would say in high dimensions, you probably want to either find the posterior distribution, or if you want to use something based on optimization, then you have to worry about overfitting, and Michelle will have lots to say about overfitting when she introduces machine learning methods which are based on optimization rather than the posterior distribution. Okay, so that's just a thing that happens to remain in these slides. I thought I would go over it. So I'm going to show you a curve fitting example, and lots of astronomy data sets and tasks that people want to do are based on curve fitting. So you've got something like noisy data, some idea of a function that underlies the noisy data, and that function that underlies the noisy data has parameters that you want to infer, and you would want to estimate the parameters and get all the uncertainties on all those parameters given the data. So I'm calling this the transit example, and it is an extremely simplified model of an extrasolar planet transit. So suppose we're observing a star over time, and we look at the brightness. Here, you'll notice I'm rebelling against my astronomy heritage by saying that higher magnitudes are brighter. So we've got the brightness of our source is constant, and then during the transit, it jumps to another constant, and then after the transit, it jumps back to its original value. So how would we fit the red curve to the blue data? Well, to do things in the Bayesian way, you would need to describe the set of potential red curves by some parameters that determine the shape of the red curve. Like maybe those parameters are to do with how big the dip is, at what time the dip begins, how wide it is in time. So you come up with some parameters that describe the things you're trying to infer. Choose prior distributions for all those parameters. Choose a sampling distribution. So what's the assumption about if I knew the red thing, what would be the distribution of the blue things? So how does the data connect to the parameters? Then you would have the posterior distribution of your parameters, which would give you the chance to estimate them. If you want to look at one of the parameters, you could find the marginal distribution of just that parameter. So say you wanted to know the depth of the transit. If that was a parameter, you would have to marginalize over all the other parameters. And that used to be tricky, but Markov chain Monte Carlo makes it easy. So curve fitting is everywhere. There's heaps of astronomy examples, so you could easily imagine like more realistic transits would be something like this, but with more realistic model assumptions than what I'm going to use. Finding emission and absorption lines in spectra, that's just fitting. We do fitting all the time. Minimizing chi-squared type fitting procedures in astronomy are very often just the same thing as maximum likelihood estimates of the parameters with a Gaussian likelihood function. So there are many examples where that's the traditional thing to do, and you can quite easily change them to be Bayesian just by applying a different algorithm to what you do with it. And you can calculate your posterior distribution instead of just getting a point estimate, which is just a single estimate of the parameters. In 2 dimensions, you might want to have an image, and you want to fit a galaxy to an image or whatever. So you've got an image of a galaxy, and it's got noise, and you want to fit a Sursich profile or whatever to that image, and the Sursich profile would have a bunch of parameters, and you could do that with Markov chain Monte Carlo. And there's a lot more than that. So I apologize for using simulated data. I know it's a bit of a cop-out, but I like to have nice little examples, especially for an introductory thing, where we know the truth. And so when we get the answers that you would obtain if you just apply the Bayesian analysis, we can kind of see that stuff comes out basically correct, although we come out with uncertainties as well. So we'll be able to see what they look like. So the true red curve that I used to generate the data set, the brightness was 10, and that applies outside of the transit, and then during the transit the brightness dropped down to 5, and the transit had a width of 2 time units. And so the goal would be to describe all these things by unknown parameters and infer those parameters from the data. So I added noise. And when I added noise, I just used the normal distribution independently for each data point and added noise. And that's a very standard assumption. That's this Gaussian noise assumption that you see all over the place. So the model I'm going to show you the fits for and the code for looks like this, and it has 4 parameters. There's 4 parameters, A, B, T, C, and W. And what they are, A is the brightness that applies outside the transit, so that was actually 10. Okay. B is the depth of the transit, so how far down did it go? Okay. TC is the time of the center of the transit, and I apologize if there are any exoplanet people here who could probably tell me that that's not the way that's not the parameterization that they use. I don't know. They might use the beginning or the center or something else, but I just used the center when I did this. So I've got, yeah? Yes, yes, thank you. Yes, my magnitude scale is backwards. That's just, yeah, sorry about that. I'm pretty sure that if I have an equation that contradicts a plot, the plot is correct. Because otherwise, how would I have even come up with that plot? And I'm pretty sure that's the data that's in the data file. So if you run anything, you should get, yeah. So sorry about that. Oh, yes, B is negative. Oh, yeah. I don't know. Yeah. Whew. Okay. It's funny because these slides, and apologies to the organizers, but these slides are actually, or many of them are a few years old, and I've sort of had that mistake in there for a few years. But obviously, I modified them and added things and took things out for this one. Oops. So this is the model I'm going to fit. It's got 4 parameters. What's the... oh, yes. Okay. The 4 parameters have to do with the brightness, the depth of the transit, the time at which the transit occurs, and the width of the transit. So this is more important than getting the exact formula right. The code should be considered the canonical version of the formula. So according to Bayes' theorem, what we're going to try and do is we're going to use the data to infer the values of the parameters. And in the Bayesian format, that means calculate the posterior distribution for all of the unknowns given all of the knowns. And all of the unknowns are the 4 parameters, and all of the knowns are the data, so the values of the timestamps and the measurements and the error bars, though I'll have something to say about the timestamps and the error bars and whether those are to be considered as data a little bit later in the lecture. So we want to get this 4-dimensional posterior distribution, and so to do that we have to assign a 4-dimensional prior distribution and a likelihood function, and then we need a way to compute or do something with a 4-dimensional probability distribution. It's not necessarily obvious what you should do with that. If you wanted to generalize what we've had in our cases of single unknown parameters where you had a grid, you could have a 4-dimensional grid of possible values for those 4 parameters and then calculate this times that on that 4-dimensional grid and normalize it if you wanted to. But that becomes very awkward, especially if you start going beyond 4 parameters. You know, dealing with 4-dimensional arrays is obnoxious, and in say 100 or 1,000 parameters, it becomes virtually impossible. So we need some other numerical way to handle high-dimensional probability distributions. First, I'm just going to show you some considerations about choosing the 4-dimensional prior distribution and the kind of things that you can think about when you need to construct that. So how do you choose the probability distribution over a 4-dimensional space? Easiest way is to break it up using the product rule, potentially make some assumptions that the priors for certain parameters are independent of each other, in which case the joint prior for all the parameters, you'll just have a product of the prior for each of those parameters. And that's usually okay. And actually we'll do something very similar for the likelihood. We'll assume conditional independence like we had last time, where the likelihood will just break up into a product of one term for each data point, and each term for each data point doesn't refer to the other data points. Okay. So in any general problem, if we had 4 unknown parameters, we could use the general version of the product rule to decompose it into separate pieces. And what it would look like in general is that if you want the joint distribution for 4 things, you could start by writing down the distribution for one of them, so the marginal for the first one, times the distribution for the second one given the first, times the distribution for the third one given the first 2, times the distribution for the fourth one given the first 3, and so on. And that's just an extension to more variables of the version of the product rule where it's like probability of x comma y equals probability or distribution of x times distribution of y given x. You can extend it out to multiple things like this. So the distribution for each one given all the ones that came before. That's completely general, and so you could, if you thought that your prior should be correlated, so say that you know the meaning of 2 parameters is connected, say, so that if you got some information about one of the parameters, that would tell you something about another one, then you would want them to be dependent, and you would need to take into account, say, that knowing A would tell you something about B when you write down what this term is going to be. But in most cases, in many cases, independence is fine. So if you assume that knowing B wouldn't tell you A, knowing TC wouldn't tell you A, knowing W wouldn't tell you A, knowing any of these parameters wouldn't tell you about anything about any of the others, then you can use independence, and you just have to assign a prior distribution to each of the parameters separately and multiply them together. And that's what I'm going to do with this. All right. So the assumptions that are in the model are relatively straightforward assumptions of just assigning wide priors to the values of things, and just going to assume they're independent. And here I've got three ways of writing down a uniform distribution. So I could write down the expression for the probability density function. So for A, which is a parameter about setting the level of the magnitude of the star, I'm going to have a uniform prior with some generously wide limits. And you could write it down as the density function, or you could just write it down for concise communication. You can write it down as twiddles. And I've usually been writing out the full name of the distribution, but also you can write down a lot of them have abbreviations that are well understood. So U, everyone would know is uniform. And for normal, you could just write N or curly N, and people would know that it's normal. So I've just assigned here four uniform priors, just to keep life simple, for the four parameters. So for A, I'm just assuming uniform from -100 to 100. So just over a very wide range before getting the data, I didn't know what A was, and I'm assuming, or one way of thinking about the uniform prior is that I'm assuming some kind of an invariance property where if you were to add a constant to everything, that wouldn't change anything, and so you're treating like the probability density is the same if you shift everything up as it was at the original level. For B, the depth of the transit, I'm just assuming a uniform distribution as well, just from 0 to 10, and that 10 is just arbitrary. One of the things that will happen as you get experience applying these things is that you might start to notice that in lots of cases, the exact choice of the prior doesn't matter that much. And that's what happens, I think what happened to a lot of statisticians in the 1990s when MCMC became popular and they could suddenly apply it to lots of problems, is that a lot of the arguments about, well, how do I choose my prior, used to cause a lot of angst. And, you know, philosophically it is a problem. And you know, there's lots to think about how to assign priors, but I think what happened to statisticians and what made Bayesian statistics get accepted more was that they just realized that actually all this angst about the priors didn't matter that much. In the vast majority of problems, it makes little difference if you have a prior, you know, that's uniform or non-uniform but wide or whatever. A lot of the time it doesn't affect your answers too much. If you find that the prior does affect your answers a lot, then the answer is spend more time thinking about your priors, but usually that doesn't happen too much. We've got, I'm hearing laughs. Okay, I should probably tell a story about a time when I did choose really bad priors, and they did affect my answers a lot, and I spent about 3 months worrying about what was going on. So during my PhD, I was doing gravitational lensing, and I was trying to come up with algorithms so say you've got a galaxy here, got a galaxy behind it, so there's gravitational lensing, and you get something like an Einstein ring. So this is the image of the background galaxy. So I was working on methods to take this image, and from this image, I wanted to infer what the background galaxy would look like if it hadn't been lensed. So what does the background source really look like? And also, what does the mass density profile of the foreground galaxy look like? So you're trying to infer kind of two density profile looking things, one for the light of this background galaxy and one for the mass of the foreground galaxy from just an image. And so I had to come up with a way of describing, using parameters, what the background galaxy might have looked like. And I was starting out using grid-based models, where I just pixelated what lensing people call the source plane. Basically, it's just what might the background galaxy look like, unlensed. Well, divide it up into pixels, and let every pixel be a free parameter. Okay, and there's something like 10,000 of them. Okay. So you've got 10,000 unknown parameters. You need a joint prior distribution over this 10,000 dimensional space of what the value of all these pixels might be. And one thing about the sky is that it doesn't suck photons out of your telescope. So you know that all these y's need to be positive. So what I did was I just said that the prior for each yi was uniform from 0, so they're all positive a priori, up to some wide maximum in whatever the units were that I was using. And I thought, wow, that's an ignorant prior ignorance, uniform distribution for everything. And what happened was that I actually smuggled in an assumption to there that I didn't realize when I was choosing that, which is that prior implies that the night sky is bright in the region of that image. Because if you take that assumption that all the pixels are independent, and they're all positive, and they might be between 0 and 1 million, and if I work out, well, what does that imply about the prior for, say, the total? You actually get a very narrow, approximately normal distribution for the prior on the total flux. So I thought I was putting in ignorance by using uniform priors. I was actually putting in a high amount of confidence that the total amount of flux in my background image was some high value. And so when I was fitting it to the data, I was getting this kind of like glowing red sky where it should have been dark. And so yeah, despite all my what I was saying here, that you know, you can usually just throw caution to the wind and choose whatever broad priors and it doesn't matter. Sometimes it does matter. And I would say that problem that I encountered is kind of a problem that becomes more of a worry in high dimensions. I would say in low dimensions, when you assign a prior, it's easy to understand what you've done and to understand the implications of what you've done. But in high dimensions, it can sometimes have freaky consequences that you didn't realize you were assuming, and that might matter. Okay. All right, so the typical brightness of the star, the depth of the transit, the time of the center of the transit. I use a uniform prior from the beginning of the data set to the end of the data set because I'm not looking for a transit that's outside the data set. And for the width of the transit, I'm looking for a transit of width less than the width of the data set, otherwise what on earth am I doing? And so I've assigned a uniform prior from 0 to the range of the data. And you can think about this for a few minutes. I'll address it later and give you the answer. It looks like I'm using the data to set my priors, and that's a no-no in Bayesian statistics because the priors are meant to describe your uncertainty, not taking into account the data. So you shouldn't use the data in them. It kind of looks like I'm doing that, but the answer to my question at the bottom, are we using the data to set our priors? The answer to that is actually no, and I'll explain why in a little bit. So there's actually no fundamental problem with what I've done using the t's in there. So that's the priors. Split it up, make everything independent. Usually a good place to start, unless you think that some of the parameters would tell you something about the other ones. And for the data, I'm writing down the sampling distribution or the probability distribution of all the data given all the parameters. So if I knew all the parameters, what distribution would I use in order to predict the data? And I've just assumed that the value of the ith data point has a normal distribution centered around what that model function would predict. So I'm just assuming that if I wanted to simulate a data set, say, based on knowing the values of the parameters, I would compute a model function and then just add Gaussian noise to everything. So that's the super standard assumption that you see all the time. And you can write it down using Twiddle's notation that the distribution of the y's given the parameters is a normal distribution, and the mean of the ith data point is whatever the model function would predict or would be evaluated to at time ti and based on the parameters. And the standard deviation, I'm just going to assume that there's a given standard deviation for every data point. It's like an error bar in the data set. If you had a 3-column data set with time, y, and error bar, this is a very standard convention to assume that the third column is the standard deviation that should go in there. So that's how I would write it if I wanted to just tell someone what I was assuming, and this is how I would write it if I actually needed to write down the equation to do something analytically, or it turns out to use the Metropolis algorithm, we'll have to implement a function that evaluates this as a function of the parameters, the 4 inputs. Okay. So the great problem that Monte Carlo, Markov chain Monte Carlo solves is it gives us a way of numerically dealing with this 4-dimensional posterior distribution that we're trying to look at. Because the 4-dimensional distribution is hard to understand and it's hard to visualize. But say we had some way of computing the marginal distributions of this 4-dimensional distribution. So there is a 4-dimensional joint posterior. You can just imagine a 3-dimensional thing with like more density in some regions than others. That's hard to visualize, but if you just wanted to look at the distribution of A, the marginal, and look at the uncertainty about A, if you had some way to just get into the 1-dimensional, the marginal distribution, that would be very helpful. And that's what Monte Carlo lets you do. It lets you take that marginalization integral, and basically you can marginalize trivially if you can use MCMC. So the answer to this problem of how do we deal with high-dimensional distributions is that instead of going everywhere in the space or making a grid across the space and calculating the probability everywhere or the density everywhere, instead what we'll do is come up with an algorithm that draws samples from that distribution. So instead of computationally representing it with a grid of values and the density, we're going to computationally represent it with just a bunch of points drawn from that distribution such that the distribution of those points approximates the distribution that we care about, and we know that by the way that we've constructed the algorithm. So we know that by the way we construct how to generate those points. So instead of coming up with, in one dimension we had an array of parameter values and an array of corresponding probabilities or densities, instead we'll just have an array of parameter values, and we'll just get more parameter values that are around the areas where there's lots of probability and fewer around the values where there's not much probability. Okay. So if I had this 2-dimensional posterior distribution and I had it in this kind of format, and I wanted to get the marginal distribution for A, I would integrate over B. I'd get this curve. If I have these points sampled from the joint distribution for A and B, and I decide I don't care about B, or I don't care about the vertical axis, all I have to do to look at the marginal distribution for A is ignore the B values of the points. So this thing that used to be an integral, you might have like a 4-dimensional function and you want to integrate over 3 of the dimensions, all you have to do is histogram 1 column of a matrix, basically, and you've done it. So that's the magic of Monte Carlo. And so the Metropolis algorithm gives us a method of how to generate these points. How do you generate just a sequence of like guesses of all the parameters such that they are sampled from the joint posterior distribution so that you can marginalize trivially and so that you can summarize the uncertainty fairly easily as well. So I suppose I wanted to calculate as a summary of my posterior distribution. I've got my 4-dimensional posterior distribution. Suppose I wanted to summarize it by giving an estimate of W, the width of my transit, and I was going to do that by calculating the posterior mean, which is just the expected value of W, using the posterior distribution to calculate the expected value. So analytically, I would have to do this 4-dimensional integral, where I've got the integral of w times the posterior, so that's the expectation formula. That's nasty, but in Monte Carlo, if I have all these parameter values sampled from the posterior, it becomes trivial to approximate that just by the average value of w in my samples. So you get a bunch of possibilities for all the parameter values, and then you just average the w's in those, and you've effectively done that four-dimensional integral. Okay. If you want to know, say, the posterior probability that the parameters are in some region, or say the probability that w is greater than 3, or anything like that, so anything that's a single statement about the value of the parameters. In the olden days, you would have to calculate the expression for the joint density here, four-dimensional thing, and to calculate the probability that you're in some region, you just do the integral over that region. So you would have to define mathematically what's that region and do the integral. But if you have Monte Carlo samples, you just have a bunch of replications of what the parameters might be, and you just calculate the proportion of them that happen to land in the region R, and if you have enough samples, that's a good approximation to the posterior probability that the parameters are in the region R. So everything that used to be an integral that was very hard becomes something very trivial, and this is the value of Markov chain Monte Carlo. Okay. There are other ways to deal with high-dimensional probability distributions. So Markov chain Monte Carlo can be computationally intensive, and there's some big problems where trying to use MCMC is practically not a good idea. I think Ewan will be covering some methods that you can use for bigger problems where MCMC is too costly. So it's not the only answer to how to compute these things, but it's a good one, and it's pretty popular. This video, if you want to click that link, that's a few years ago when the Harlem Shake was a viral video. There are a couple of MCMC-based jokes about the Harlem Shake that you can look up. Should have updated that and using whatever's the most popular thing these days, like maybe that, if it was a couple of months ago, it could be that one with the guy and the two women, and he's looking at the wrong woman. Actually, maybe, yeah. I just had an idea of what I should have had at the beginning when I was dissing MC, but it's too late now. Okay, so this is the Metropolis algorithm. This is a recipe for how to generate points from the posterior distribution. So how do you generate guesses of the parameters such that the proportion of your guesses that are in any region is approximately the same thing as the probability according to the posterior distribution of being in that region? It's quite straightforward. So you start somewhere, you have a position that's in the parameter space, so just an initial guess of what the parameters might be. And then there's just a recipe for moving that guess around. And it's a Markov chain, which is a term from probability theory, which is what happens when the distribution for where you are at one time only depends on where you were at the previous time, and it doesn't depend on any earlier history than that. So within this loop, there's a recipe for how to go from a certain point to the next point, and the recipe for how to go from a certain point to the next point doesn't depend on anything other than what the current point is. Okay. So you start somewhere, and then you use something called a proposal distribution, which is just something that you have to come up with to describe, given where I am, where might I go next? So it's a proposal distribution because it's used to generate the possible next state that your point should go to. And a very common proposal distribution is to take wherever you currently are in your parameter space, choose one of the coordinates, and then just move that coordinate a little bit to the left or a little bit to the right using some symmetric distribution around where you currently are. So you could put a Gaussian centered where you currently are and then just draw from that Gaussian. So it's just like just a slight mutation to the current model. So you've got where you currently are, you've got your proposal distribution, and then there's this acceptance probability, which is the key feature of the Metropolis algorithm. It's that you generate, you've got where you are, where you might go next, and then based on the properties of where you are and where you might go next, you either go there or you don't. So if you go there, that's called accepting. And if you don't go there, that means the proposal is rejected. And in the case that the proposal is rejected, you stay in the same place. And you call that one iteration. And even if you're in a position and your proposal gets rejected, you stay in the same position, and that gets counted again in your results. So how do you determine whether to accept or reject? There's this Metropolis Rule, which is gives you the acceptance probability alpha. And alpha is the minimum of 1 and this ratio. So basically what it means is you look at this ratio, which is the value of the prior at the proposed point times the likelihood at the proposed point. Basically, how good is the proposed point? How plausible is it? Divided by how plausible is the current point. And if your proposal is better than the current point, then you always accept. So that's what the minimum of 1 and this ratio is doing. So if this ratio is greater than 1, meaning the proposal, theta primed, is better than the current position, theta, then this is a number that's bigger than 1, but acceptance probability can't be bigger than 1, so it just becomes 1. That's what the min is doing. If the proposal is to go uphill, you do it. If the proposal is to go downhill, and this is what makes MCMC not an optimizer, if the proposal is to go downhill, then there's an acceptance probability, which is to do with the ratio of how good the proposal is to how good the current position is. So if your proposal is to move from some position here to some position over there, and you measure that that's 20% as good, then you generate a random number between 0 and 1, and if it's less than 20%, you go there, and if it's not, you stay here. So there's some chance of going downhill. Okay. So that's it. So that translating that into code is implementing the Metropolis algorithm. And when you want to apply it to a certain problem, what you need to do is just give it some functions which let it evaluate the goodness of the proposal and the current point. So that's just a function like that evaluates the prior at any given position, and a function that evaluates the likelihood at any given position. And you just need to also choose a proposal distribution. So what's the rule for what point might I go to next, given where I currently am? Okay, that's not actually the fully general acceptance probability formula. I made a specific assumption about the proposal distribution, which is that it's symmetric. And symmetric means that if you're in a current position and you propose to go to some new position, the probability of generating that proposal given where you currently are, if that's the same as what the probability would be of the reverse, so if I was in that proposal position, what probability would I propose to come back to where I currently am? If those two things are equal, then the proposal distribution is said to be symmetric. And in most of the examples that I've got for this, Q is symmetric. So the very common example of just choosing a coordinate and then applying a normal distribution around the current position is symmetric. If it's not symmetric, then you need to put in this extra ratio, and that's just to compensate for the fact that if you have an asymmetric proposal distribution, you're kind of biasing things by saying that you're more likely to go from here to there than from there to here. You need to somehow cancel that out of the final results, and so the way you do that is to put the ratio of Q's into the acceptance probability. So the Metropolis algorithm it's kind of a shaping kind of algorithm. Your proposal distribution, if you just let it loose, it would just go everywhere, basically. But by strategically putting in boundaries, like you're trying to go from this good place to this bad place, and by saying no, it kind of shapes the distribution of the points that you generate into what it ought to be. It's really quite cool. Okay, so to apply it, you need to specify some functions. So I mentioned this just before. So you need to decide somewhere to start. So if you have a good estimate of the parameters, like you optimized, you did some other fitting process, or you can see, you know the meaning of your parameters, and you can see obviously approximately what they're going to be, or whatever, you can set a good starting point for your parameters. Otherwise, you can just generate a value for the parameters from the prior distribution, and a lot of the time that'll work out fine. It basically just means that there'll be a part of the algorithm at the beginning when you run it that will go where it will be basically looking like an optimizer, going from somewhere that sucks to where most of the posterior probability actually is. So you need to be able to generate a starting point, be able to make proposals, evaluate the prior distribution at any point, and evaluate the likelihood at any point. Okay. So in the repository, so for those of you who had the issue cloning the whole repository, there was some issue. People couldn't use the recursive thing, so they couldn't get this code with their clone command. If you want to get it, this will be the URL, and let me know if I need to enlarge the font. Is the font big enough for people to see? I'll just enlarge it anyway. And Ewan will recognize this URL as, so that's a clone of something I did for him years ago that didn't really go anywhere. But it's a Python implementation of nested sampling, which I'll come to soon, but it's also got Metropolis code in it. So I'll just wait a few more seconds in case anyone's typing that in. I'll go to where it actually is on my computer. Oh, I already had it open, so I didn't need that. I'll increase the font of this as well. Okay, so I'll just walk you through. So there's a file in that directory called, actually I think you have to go cd python inside the repository. And there's a file called plain_metropolis.py, which is Metropolis code. And so I'll just walk you through the lines. If you know Python and NumPy and stuff, they should be relatively straightforward. If you don't, they should be approximately straightforward and should be reasonably easy to implement this in whatever your favorite language is if you want your own version of it. So at first I've just got some import statements. I'm just going to be using some libraries, so need that stuff. And then if you want to, you can set a random number seed so that every time you run the algorithm you get the same results if you need to debug or anything like that. Otherwise, if you don't do that, every time you run it you'll get different results because Monte Carlo method. Now I'm defining some functions, or I'm importing some functions from another file, and that's all the model-specific stuff. So in the file transitModel.py, I've got the definitions of these functions. They're called fromPrior. That's a function that generates a random vector of parameters from the prior distribution. That's actually more useful in nested sampling than it is in Metropolis, though I am using it here. Also, logPrior, that's a function where as input you need to give it a vector of the parameters, and the output should be the log of the prior density. The log is to avoid the overflow and underflow problems that you could get if you didn't use the log. The log likelihood, very similar. As input, it needs to take a vector of parameters. Usually it's going to be a vector of parameters or an array of parameters, though if you have a different structure to your model where there's like different dimensionality every step or something, then code should work the same, whether these take vectors as arguments or something else. But I'm just going to keep speaking in terms of models with fixed numbers of parameters. Proposal, that's a function that takes as input the current position and returns as output the proposed new position. So if you pass in like a vector of, say, all zeros for all the parameters, then proposal should do something like pick one of the parameters and modify it with the normal distribution and then return that modified one. So that's generate from the proposal distribution, and also just the number of parameters. So this code is designed to output a 2D array where each row is a possibility for the vector of parameters. And so if you want to generate, say, 1,000 points and you have a 4-dimensional problem, then you'll have a 1,000 by 4 matrix as your output. So it's 1,000 possibilities for what the 4 parameters might be. Now you have to decide how many steps you're going to do, and in principle this should be as high as possible, but in practice, well, it's problem dependent. Some problems you can just do a few steps and it's fine. I like to do 1,000,000. It's kind of a good default. And so that determines how long it's going to run for. And then thin is something to do with how frequently you should save the current position into the output 2-dimensional array. Because if you had, say, 1,000 parameters, and then actually your problem's probably quite hard. If you have 1,000 parameters and you want to do 100 million steps because it's a hard problem, you don't want to end up with an output matrix or a 2D array that is so huge that you run out of RAM or anything like that. So thinning just means I'm only saving every 100th iteration into the final output. So those determine what problem am I working on, how long am I going to run for, do I want to not save every single point. And so the rest is just the algorithm. So we start somewhere, propose to go somewhere else, calculate the acceptance probability, accept or reject, and then do that over and over again. So start somewhere, and I'm just calling particle, that's just the word I like to use for the point that's in my parameter space that I'm going to move around. Other people call it just the point. Sometimes it's called a walker. I just like particle. Just think of it as a little particle that moves around. So you start somewhere, measure how good it is in terms of how high is the prior density and how high is the likelihood. And it's going to be the product of those two that is really how good the point is. Because we're dealing with logs, it'll end up being the sum that is used. So there'll be things involving log p plus log l. Okay. Then I am setting up a 2D array just to put the output in. And it is useful to keep track of what proportion of the proposals were accepted and what proportion are rejected. So this is just a counter of how many proposals have been accepted. Because it turns out that you don't, when you first learn Metropolis, it sounds like, oh, you want a lot of proposals to be accepted. But you actually don't want that because it's the accepts and rejects that smash the trajectory of the particle into the right shape. If you're accepting everything, then your prior and likelihood have not had any impact on the progress of your particle, and that's bad because the whole point is that your prior and likelihood should determine where your point goes, so you get the right distribution. So you don't want to accept all your points. You also don't want to reject all your proposals, because that just means your output will just be the same point over and over again, and that's bad. You want something that's kind of within plus or minus an order of magnitude. You want something that's about 0.5. There'll be some people that claim that there's some paper from a while ago that says that you should try and get the acceptance probability to be exactly 0.21 something, some crap. I'm like, no. I should probably read that paper so I actually have a basis for criticizing it, but just it seems so absurd. It's like you want to tune your acceptance probability to 4 decimal places. Yeah. Okay. So then the main thing is a loop. So this is just a translation into Python of what was in that loop on the slide. So I'm proposing a new position. So chuck in my current position to the proposal function, get a new position, measure how good it is, so evaluate the likelihood and the prior. I've just got a little thing here that says that if the prior density is 0 at the proposed position, then don't even bother trying to calculate the likelihood. So if you don't do that, then sometimes if you propose, say, some parameter that has to be positive, and you propose a negative value for it, then the log likelihood might return a nan or something, and annoying stuff happens. So if you propose something that's out of bounds, then don't even bother with the log likelihood, because even the prior is going to cause a rejection. This is the ratio. So that's prior times likelihood of the proposal over prior times likelihood of the current point, but all in terms of logs, so everything becomes plus, and then log prior plus log likelihood of the proposed point minus log prior plus log likelihood of the current point. And that's going to be the log of the acceptance probability, so I'm going to have to exponentiate it at some point. But before doing that, I'll make it so that if it's positive, then it's 0, because otherwise, sometimes you might get, if you're starting at a terrible point, you propose some point that's like e to the power of 1,000 better, then if log a is 1,000, then when I exponentiate it, I'm going to get an acceptance probability of e to the power of 1,000, which will become infinity, and all sorts of nonsense happens. So if the log acceptance probability, if the log of that ratio is positive, just set it to 0, because it's still going to accept anyway. Okay, this is the acceptance. So if a random number is less than the acceptance probability, so that's something that has probability alpha, which I'm calling A in the code, or log A is log alpha from the slides. If you accept, then the particle position is the proposed one, and how good it is, we've already measured that, don't want to have to evaluate it again, so may as well just copy it from what we've already got, and increment the counter for how many times it was accepted. That's it, that's Metropolis. Loop a bunch of times, chuck results into that matrix, and then at the very end, save that matrix into a file. And so it's going to be posterior samples.txt, and then I've got some plotting at the end. So I can run that, and it should be pretty straightforward to run, just using Python 3. That's plain metropolis.py, and if you're using Anaconda and Python 3, there shouldn't be a problem. My computer's a bit old. And there's a little message that prints out how many iterations it's done. That's slower than I thought it was going to be. Gives me a chance to rest. I've only got half an hour more, so I'm going to have to rush a little bit. So we might have to not do examples or questions. So I'll just show you some of the outputs that you can get from this, and then I'll move on to nested sampling. And if you want to, you can run a couple of other examples that are in the repository. Okay, saving the output. That's just going to be space delimited text. Now what this is plotting is what's called a trace plot, which is just a technical name. It's kind of around the place. On the x-axis is time or iteration, and on the y-axis is any one of my parameters or anything that is a function of those parameters. So if you want to see how your point moved around in terms of one of its coordinates, you could just plot one of the columns of the output matrix. In this case, I'm just plotting because I didn't want to arbitrarily designate the first parameter or the second parameter as the one that gets plotted by this code. I'm just plotting actually the log likelihood, which is kind of the goodness of fit, as a function of time. So if you were doing an optimization process, your log likelihood should just go up until you've got to the peak, and then it should stay constant. So you would just get a curve that just goes up. But MCMC is not for optimization, it's for sampling. So you're trying to find a bunch of models that basically fit. And so instead of just log likelihood that goes up, you get log likelihood that jitters around some plausible range that all means reasonable fit. And you could plot this as a function of, so you could plot columns of your output matrix, and each of them should give some kind of plot that looks like this. Okay. Now, in the transit model.py code, this is the bit where there's a bunch of stuff that implements the assumptions of this specific model. So I've got some, I'll just go through that quickly. How many parameters are there? So I'm dealing with vectors of length 4 to represent points in the parameter space. There's data, so I'm loading the data, because obviously the log likelihood function is going to involve the data. Just for convenience, I'm defining things like the range of the time in the data, stuff like that, just for convenience. I'll skip jump sizes for now, because there's slides about that. Got a function. By the way, if anyone's a Python expert, I'm just using this. I don't know how to write fast Python. I really suck at it, and I thought, well, maybe I'll try and learn how to use this number thing that's supposed to make your Python fast. And I don't really understand how that works either, but it seems like if you put this JIT in front of every function, it's supposed to go fast. So I tried that, and sometimes it goes fast and sometimes it doesn't, and I have no idea what's going on. But anyway, that's why I've got this JIT in front of all my functions. Now, yeah, just-in-time compiler, yeah. I knew that much, but I didn't. Apparently there's judgment calls, and you're not supposed to just spray it everywhere, but whatever. Yeah. Okay. From prior, I'll skip that true, actually, because here I was just using that to generate some initial point. So I need a function. It needs to be called log underscore prior that takes as input a vector of parameters. So it's just going to be an array with 4 elements, and returns the value of the prior density at that point. So all our priors were uniform, and a uniform density has just a constant value if you're inside the range and 0 outside the range, and this is log of that. So it needs to return some constant value if you're inside the range, and minus infinity if you're outside the range. So all I'm doing actually is returning 0, which is a constant value, and if the parameter that comes in, if the parameters are outside the range, in terms of any of the parameters, I return minus infinity. And since the Metropolis algorithm is based on ratios of prior times likelihood, if you have any constant factors in your prior, like the uniform density might have a value of 1 or a value of 2 or whatever, depending on how wide the uniform prior is. Doesn't matter in here. You just need the bit that actually depends on the parameter values. So as a function of those parameters, the density doesn't change, so I'm just returning 0. The log likelihood is the log likelihood. It's basically the goodness of fit. So I'm using that normal distribution, so normal distribution for every data point, centered around what the model would predict based on the values of the parameters. So parameters come in as a vector. I just unpack them to give them convenient names. So I've got 4 scalars. Calculate the function, which is the model, basically the red curve from the parameters. And then return something that's basically minus a half chi-squared of the parameters from the model, which is something that happens when you're using the normal distribution for your data. So if you have a normal distribution assumption for your sampling distribution, then the log likelihood has minus a half chi-squared in it. So anyone who's been doing that kind of fitting, it's very easy to translate it into this, because your chi-squared function, it just becomes part of your log likelihood. if some of your unknown parameters relate to the variance or the error bars or the standard deviation term rather than just the mean term in the normal distribution, then you need to also remember that there's 1 over sigma root 2 pi in the equation for the normal distribution. And if sigma is something to do with your parameters, then you must have that term in the log likelihood or you'll get things wrong. Okay. So this bottom part is basically minus a half chi-squared. Top part is the 1 over sigma root 2 pi stuff for each data point. And it's a sum over all the data points because the likelihood itself is a product over all the data points, and this is the log. The proposal distribution is the thing where the input is a current position of the parameters and the output is a perturbed version of it, of the input. And Python has that weirdness where if you say y equals x, then y is literally x. You didn't make a copy if you just say y equals x. And so you have to do fancy stuff to make a copy because you can't destroy the original position that is given to this function because you might be rejecting the proposal, in which case you need to go back to the original position. So you definitely need to make a copy. And then I'm choosing one of the parameters at random, and then I'm adding some random perturbation to it, and I've got some kind of size indication of how big those jumps should be, and some kind of weird distribution for the distribution of them, which I'll just discuss very quickly here. So a problem that happens with the Metropolis algorithm in many cases is that you have to worry about how wide your proposal distribution is. So suppose you had your posterior distribution in 2 dimensions, looked like this, and so there's contours of the density, and you're doing Metropolis, so you start somewhere, propose to go somewhere else, and I'm just doing horizontal or vertical proposals, 1 coordinate at a time. If your proposal is a normal distribution centered around where you currently are, and you make that standard deviation of the normal distribution narrow, then what happens is that you'll only ever take very tiny steps. And you won't move very far, and you'll need so many iterations, and it'll look like that. And eventually that'll work fine, but if you look at a trace plot of it, so say you look at time or iteration on the x-axis and the value of x on, or let's make it the value of y on the y-axis here. Then the way it would look is kind of like hardly going anywhere, and then when you do go somewhere, you're just as likely to erase it and go backwards again, and you end up with a trace plot that looks like kind of rubbish. The movement is so slow that you can just see, if you know anything about time series and autocorrelation, there's heaps of autocorrelation. So you don't want to see that, and that's a good diagnostic plot to make. If you have a proposal distribution that's too wide, so say my proposal distribution is to choose either x or y and perturb it by adding a normal distribution random variable to it with a very wide standard deviation, then so I might propose to add 1,000 to this, to the x coordinates. I'm proposing to go way over there. That's a crappy point, so reject it. Basically, you're proposing to move too far in one step, and you're going to reject a lot of things, and you end up staying in the same point a lot. So that's bad. Step size is too small. If your step size is too big, you'll just stay in the same place because you're proposing all this nonsense. It doesn't fit. And occasionally, you'll just, well, that looks like it came back to the same point. That's misleading. Okay. That's also bad. If you have a Goldilocks kind of step size, then you'll end up with something that looks like more like white noise. And that's good. So what a lot of people do is they fiddle with it. They start out, and by the way, you could also look at the acceptance ratio, so what proportion of the proposals were accepted, and this would give a high proportion, low proportion, and a medium proportion. And what people do is they just twiddle with how big their steps are in each coordinate and then try and optimize them. But I'm too lazy for that. So I do something different, which is I randomize the step size. So instead of like running 10 runs and twiddling, may I make my steps a bit bigger or a bit smaller, I'm just like, bugger it. I'm going to do some mixture of step sizes. Sometimes they'll be huge, sometimes they'll be small. Some of the time they'll be right. It'll be less efficient than a tuned run, but I won't have to do any tuning. I just run it once. So what I've done is, or what I used to do actually is have a random value for the standard deviation of the proposal. So how big am I going to jump? Roughly is this L, and I would vary L every step. And I have almost the same thing in the file here. I've got something called jump sizes, which is different value for each parameter. It's basically how wide's the prior for each parameter, because you're not going to need to jump bigger than the width of the prior, because the posterior is almost always narrower than the prior. And so the jump sizes set a kind of maximum distance that I would want to jump on each step for each coordinate. And rand_h is something that I've defined in one of the other files in the repo, which is just a heavy-tailed distribution that says my jump size will kind of max out at about the value in the jump sizes vector, but it might also be like 10 to the minus 3 or 10 to the minus 6 or 10 to the minus 12 smaller than that. So it's a distribution which is like a normal distribution of unknown standard deviation, which is sometimes a lot smaller than 1. 15 minutes, yes. I don't even know if I'm going to... Well, I probably won't have time to do nested sampling, unfortunately, which is a shame. But my slides are there, and if anyone wants to ask about it, that's would be appreciated, and I'm happy to talk about it. So that's what the proposal function does. And the proposal function that I've got in that transit model.py is pretty generic, and I think in the other examples that are in the repository, it's basically the same proposal function. You just need to define the jump sizes array to say, roughly what's the maximum distance I'm ever going to jump or try to jump for each of the parameters. So I'll just show you a few useful little bits of code for how to handle MCMC output. So what plots can you make? How can you compute summaries of the posterior distribution? So like you want to say the parameter is 3 plus or minus 1. How would you compute those numbers? So the posterior mean and standard deviation, say, or if you want to present an interval as your conclusion. It's usually quite easy to do things like that, and this is one of the beauties of MCMC. Once you've got your samples, that's the hard part done. Everything else is easy. So what I've got is I've put the output in posterior samples.txt, and that is just a 2D array of space delimited parameter values. Each row is one possible value for all the 4 parameters, and so each column is a collection of possible values for one of the parameters. So if I want to load that, I can just use numpy.loadText.
Sorry, let's see if I understood. You created a million possible steps. Some of them were accepted, some of them were not.
Yep.
You took one every 100,
yep,
and that's what you stored.
Yep.
Okay, so if you had stored all of them,
yep,
some of them would have been repeated, because in some cases the new step the new position would have not been accepted. Is that?
That's correct.
Okay.
Yep. So at first it seems weird to have like duplicates of the same point in the samples, but it's actually fine. It's how it's kind of how, this is how I explain it to my undergrads, and they accept it. So we'll see if it flies here. If a point is good, has high probability, right? So if it has high probability, you want it to contribute a lot in your results. So the way the Metropolis algorithm says a point is good is by rejecting a lot of proposals to move away from it. So that point will appear several times. Whereas if a point sucks, then pretty much the first proposal away from it that doesn't suck is going to get accepted. So points or regions where the probability is low, it's really easy to get out of them and hard to get into them. And regions where the density is really high, once you're in them, it's a bit hard to get out. And that fact is what makes it become overrepresented in the output. By the way, since I'm not going to do nested sampling, I may as well tell you. I don't know if anyone knows Geraint Lewis from Sydney University, but he was my PhD supervisor. And I don't know if he knew the Metropolis algorithm when I was just starting out using it. But for the longest time, he thought that the reason that it was called the Metropolis algorithm was that when you make a trace plot, it sometimes looks like New York City or something. But that's actually not the case. So you get the skyscrapers when nothing was accepted for a short amount of time. And I thought that was hilarious because it's actually named after a guy called Metropolis, who was a physicist or chemist or something in that realm. And someone came out with a history of the Metropolis algorithm, and apparently, so he was first author on the paper, but apparently he didn't have much to do with it apart from provide the computer. And the computer, this was in the 1950s, so having a computer, I guess, was super amazing. Anyway, it's the Metropolis algorithm. You also see it called the Metropolis Hastings algorithm. I'm not sure if this is 100% correct, but I think what happened was the Metropolis algorithm kind of had the so statistical mechanics, so they didn't have like prior and likelihood, they just had energy. And they just had in their acceptance probability the ratio of two energies. And I think what Hastings did was notice that you could have asymmetric proposals and put in the Q ratio into the acceptance probability. So sometimes you see people say it's the Metropolis algorithm when you have a symmetric proposal, and it's the Metropolis Hastings algorithm if you have an asymmetric proposal and put the Q's in the ratio. But I think that's just a bit picky. I'll just call it Metropolis. That was a bit of a digression. Back to the output. So I can just load that 2D array. All right. And I can look at, say, the zeroth column of it, because start with 0 in Python. So this is the first parameter, posterior samples of the first parameter moving around over time. And it's got this weird glitch at the beginning. And the glitch is just that the starting point I gave was very bad. So I didn't initialize somewhere that's kind of typical of what the posterior distribution says the parameter should be. So for the very first part of the algorithm, it kind of was behaving like a bad stochastic optimizer. So starting somewhere terrible, peak is over here, and it spent a bit of time going from the terrible to where the peak was. So this, it is quite fast, but remember I had thinning of 100, so 1 on this plot was actually 100 iterations. So if you have such a thing in your plots, definitely make these plots, and if you have such a thing at the beginning, because your starting point wasn't great, then what you usually do is you call that burn in, and you just remove it from the output, so you don't use it for any subsequent summaries that you might make. Because say I wanted to summarize this distribution, so this would be a point moving around from the marginal distribution for the first parameter. So if I want to present a summary of that, I might just take the average value of the parameter and the standard deviation, and that would approximate the posterior mean and the posterior standard deviation. And if I do that and leave this point in, this point is going to drag the mean down a bit, and the standard deviation is going to get wider than it should be. So it's a good idea, if you see something like this, to chop it off and just use the bit that looks good, and the bit that looks good should look like this. And one of the lecturers in my department says that it's a caterpillar. So that's the bit you want to use. And then you use that bit to make all your summaries. So the true value was 10 of this parameter. And the posterior distribution, what you usually expect to see and what you hope to see is that if your posterior distribution looks like this, say, and you were to later find out the true value, you would hope it would be somewhere not that ridiculous according to the posterior distribution. Once I had a student who said, shouldn't the posterior distribution peak at the true value? And I thought that was amusing because I wish it worked like that. Because if the posterior distribution peaked at the true value, then you should just replace the posterior distribution with a delta function at its peak, and then you would know the true value. And there'd be no use for Bayesian inference, and I could retire because you could get the answer to everything with no uncertainty. Okay. So that's a trace plot. You definitely want to do those. If you want to look at the marginal distribution for the first parameter, say, you can just look at a histogram of the values in the first column of that matrix. And I said here, excluding the first 2,000 points, so excluding the burn-in, which I actually forgot to do in that code, but I'll do it here. Histogram of that column, and I'll just go 1,000 to the end. And voila, so you've had 4-dimensional distribution, but you didn't have to do any integration. All you have to do is only look at one column, and you've effectively integrated out 3 dimensions, which is awesome. If I want to summarize that distribution, I could calculate the posterior mean and the posterior standard deviation. And because this is a Monte Carlo process, these are not exact. It depends on how long you ran the algorithm for. But usually, I think if you read David Mackay's book, which is a really good book, Information Theory, Inference, and Learning Algorithms, you can get it free on the internet. He has a section where he claims that you don't really need more than 12 posterior samples. And his reasoning was basically that, you know, these two numbers, they're telling you the uncertainty that you have about this parameter A, which was the mean level of or the kind of base level of that star's brightness. And basically the conclusion is 10.1 plus or minus 0.21. And the reason he said you needed only about 12 samples really is that if you get these two summaries a little bit wrong, it doesn't matter, because 10.1 plus or minus 0.21 is basically the same thing as like 10.06 plus or minus 0.24. You don't usually have to stress that much about the error bars on your error bars, because they're error bars. So if your error bar is off by 10%, who cares? So some people like to run their MCMC so long that their histogram looks ultra smooth and they have 1 million points or 10 million points, and they're all so independent and the histogram looks beautiful. Basically, I would claim that if you are able to generate so many points that histogram looks beautiful, like better than this, like super smooth, then you're not working on a hard problem, and I'm not impressed. So. A hard problem is one where it takes 2 weeks and you may have like 20 samples, kind of. Yeah. So I just had a PhD student graduate who was working on phylogenetics, which is how to take genetic data of the current genome sequence of some species and try to infer from that what the ancestral tree looks like of those species. And because of the tree structure that you're trying to infer, the parameter space is really nasty. It's kind of discrete in weird ways, but also with continuous parameters in there. And he applied nested sampling to it, and it was good. But a lot of the times, these people in this field, they run MCMC for a month, and they get a trace plot. And the trace plot looks so bad. It doesn't look like a fuzzy caterpillar. It looks like just that bit of this from like a month. And then they say, well, that's the best we could do, so we'll just say those were posterior samples. Maybe they did get 12, and it's fine. Okay. Marginalisation is super easy, just look at the column that you want. It's a four-dimensional posterior distribution in this case, and you could marginalise over 3 and look at one of them, like we just did, or you can marginalise over 2 and look at 2 of them. So if you plot the 0th column against the first column, what you're looking at is it's kind of joint and marginal. You're looking at the posterior distribution for the first parameter and the second one, and I'll just plot it as dots, and I'll make a small marker size so that it looks okay. Where did my plot go? Didn't want to overplot it. Okay, so that's a joint distribution of those two parameters. That's the posterior, but for those two. This point over here is messing things up, so this is from the burn-in as well. So I can just look over here where all the points, the important ones really are. And that's kind of a nice way of visualizing the results about 2 of the 4 parameters. So it's hard to look at a 4-dimensional distribution, but it's easy to look at 1 and 2, sometimes 3, and you can get any of the 2-dimensional joint posterior distributions, but they're also marginal because you marginalized over the other 2, just by looking at the columns that you want to look at. Now it's correlated, which is kind of interesting. So this parameter was A, the kind of normal brightness of the star, and this parameter is B, which is the depth of the transit. And the positive correlation is basically, astronomers call it a degeneracy sometimes, when there's a correlation in the posterior distribution. It just means that basically there's combinations of these 2 parameters that fit. So you could have one parameter go up a bit, but then to make it fit, you need the other parameter to go up a bit. So this depth parameter was actually, if you increase it, the things get deeper. So basically, this positive correlation here means that if A goes up, then to fit the data, B has to go up a bit too. So you've got the kind of that dependence in the posterior distribution. One thing that messes up MCMC a lot is if the posterior distribution has a strong correlation in it. So if the degeneracy is so bad that it's a really thin, possibly curved distribution, then the proposal distribution that I'm using is bad, and the best way around that is to use a different method, such as nested sampling or Hamiltonian MCMC. So Hamiltonian is basically designed for the situation where the distribution is correlated. Okay, I think I've just got one more thing I want to say. Okay, there's something called a corner plot. You can look that up. That's just all the marginal distributions for one variable and all the marginal distributions for each pair. And there's a package you can use to make it look good. And one other kind of summary which is useful, so I've been saying mean plus or minus standard deviation, and that's really good. If your posterior distribution looks like a Gaussian or a normal shape, then that's fine. And that will contain about mean plus or minus standard deviation will contain about 68% of the posterior probability, which is like what we colloquially say is a 1 sigma error bar. If you want something that's like a 1 sigma error bar, but your distribution is not Gaussian looking, like if it's very heavy-tailed, you have a heavy-tailed posterior distribution, the mean and the standard deviation will be affected a lot by the tails. So you might want to do what's called a credible interval, which is like a Bayesian version of a confidence interval. You want to find the value, 2 values of the parameters, such that within those 2 values there's a certain amount of probability, and usually you want to say that outside that range you've got the same probability outside on one side as you have outside on the other side. So if you want to make a 68% credible interval, then for a single parameter, you just take that parameter, sort it, and find the value that's 16% of the way along, 84% of the way along. By definition, between that, you've got 68% of the points, so that gives you a credible interval, which is a good kind of way of summarizing your results. And a lot of people will do the thing now where they'll make a credible interval, and then they'll write something like 3 plus 1 minus 2, or something. You see that in a lot of abstracts. So it's 5:30, and I think I might just stop there. I'll be around all week, so if you want to know more about what's in the later slides, feel free to just ask. So thank you.